Well, good morning, both of you. I've got this
Good
announcement.
morning.
Thank you. I've got this announcement to from our tutor. So let's get that out of the way. Make sure everybody knows about it. She's going. Erin Nitz is our tutor, and she's going to be having a study session tonight, 7 to 9, in our classroom. And then she also mentioned, I think it's because of the turn of the semester. I think Erin Nitz has to stop being tutor. Anyway, the new tutor listed on the bottom, Sarah Snyder, um, she's planning on Thursdays from 7 to 9. So want to get those announcements made. I'm going to be sending that by email also, but just got that yesterday. And this is my first chance to tell you about it. Welcome, Maria. So I just wanted, everybody got that announcement? Okay, so what would you like to go through today? There are a couple, there's one thing I want to point out first. Yesterday when we were going through questions regarding the mean value theorem, remember we did number 13, this problem? The idea here is, okay, there's an interval that they give you. In the case of this number 13, it was from 1 to 8. And this is the mean value theorem, so 2 points can be of different heights, and you're guaranteed that the derivative shows that somewhere in between, it's got to be at least once at that slope. So the first thing you do is you find the slope of the two, you find the 2 points, and you find the slope, which we found was 3/7. Okay, so we found the slope was 3/7. Then the question was, when does the derivative equal 3/7? And so then we found the derivative of our function, x to the 2/3. We set it equal to 3/7. And then we were able to find, oh yeah, there's at least one point where the slope is equal to 3/7, and it's located at 14/9 cubed. Okay, so anyway, now, in the directions for this, it says, if the mean value theorem cannot be applied, if it can be applied, find the value where it can. So in other words, they're kind of implying that some of these might not be. So number 15 is one of those. If you look at number 15, the problem is down here on the bottom, the absolute value of 5 minus x, and the interval is from 2 to 6. Well, this one can't be done. And the reason? Oh, it's an absolute value. And you know that an absolute value, if you think about it, the absolute value graph has a cusp in it, which means, and the cusp is at 5, right? Because if you plug in a 5 for x, that's going to give you a 0, and that's where the cusp is. And 5 is somewhere in the interval between 2 and 6. So the problem is this one is not differentiable at all points between 2 and 6. And so, that one could not be done. I believe number 16 is one of those also. That doesn't mean I'm going to give you one of these, but it's something, we assume everything is going to work just fine, but they say clearly in the directions if the mean theorem can be applied. So here we have number 16, 2x minus 3 times the square root of x, interval -1 to 1. The problem here is not that it's not continuous, because you know what happens as soon as you plug in a negative, we've got a problem underneath the square root sign. And you notice this interval includes up to and including -1. So anything negative here, the function is not continuous. Therefore, I'm sorry, I can't use the mean value theorem. So I just wanted to point out to you, don't make an assumption right away that everything's fine. Make sure you check. You know, that if is a big word there. If the mean value theorem can be applied. You know, and then other problems like number 17, cosine, x minus cosine, that's continuous. We don't have a problem there. And the interval is from negative pi over 2 to positive pi over 2. So that one you're going to be able to do. And then, you know, so then you take the 2 points, you find the slope. Yeah, and this is a little bit hidden. So let me show you what's going on here. Okay. So they've got this f of b, you know, this y2 minus y1 over x2 minus x1, and they grossly simplified this. So let's just take a few minutes to show how that really works here. So when you're plugging in pi over 2, you know, here's the function. So you got pi over 2, and then you got minus the cosine of pi over 2. What's the cosine of pi over 2? I'm waiting for an answer this time, guys.
Cosine of pi over 2. Isn't that square root of 2 over 2? Or excuse me, no, that's pi over 4. It'd be 0.
That's correct. So you got this going on. Okay. And then we got to do f of a. F of a is negative pi over 2. So we have negative pi over 2. And then minus the cosine of negative pi over 2, which is again 0. So that's all going on the top. On the bottom, you just have pi over 2 minus a negative pi over 2. So this is really what this fraction should look like over here. Anyway, pi over 2, it does turn out to be pi over 2 minus a negative pi over 2 on the top, and the same thing on the bottom. So you get pi on top and pi on the bottom, and pi over pi is 1. Once you know that's the slope of those two endpoints, now you can take your derivative, which is right here, and set it equal to 1, that slope, and you can see that sine c has to be 0. And when is the sine of c 0? Actually, it's more than it also happens when you're at 180, but that's outside the realms of the segment. So okay, so that one I looked at for a while, and I didn't see how they had gotten the numerator, but really, if you look off to the right here, that's how that occurred. Okay. So I just thought I'd add that. We didn't, and somebody, let's see, there was another thing somebody asked me about. Oh yeah. Someone in class, after class, had asked me, what about absolute values? And, you know, here I have some wisdom for you about absolute value. Can you differentiate an absolute value? The answer is yes, you can, but you got to break it into two parts. The part that, you know, when 5 minus x is a negative and when 5 minus x is a positive, but then you realize, oh, wait a minute, at 5, we got a cusp. So if 5 is included in the interval, and it is here 2 comma 6, then I'm wasting my time. You can't differentiate at a cusp, so why go through all the process of finding the derivatives? Okay, let's see. Can we do number 18? Sure. Thank you, Maria. So here's number 18. It's another one of those mean value problems. Okay, so we've got a log situation here. And a logarithm is a continuous function as long as we're in the interval and we don't go to the, don't go negatives. And notice we don't. The interval is +1 to +2. So here's our function, x times the log base 2 of x. So that's a product rule. We got a multiplication sign there in the in between. Let me make that a little bit bigger. So we got a multiplication sign. So the first times the derivative of the second. Oh, well, first they rewrote it. Okay. Yeah, that's interesting. Anyway, I would have gone the first. Let me just write this off to the right. F prime. The first times the derivative of the second. How do you take the derivative of that? Well, it's 1 over that thing. But besides being 1 over that thing, you've got to multiply the denominator by the natural log of the base. And the natural log of the base was 2. Okay. Plus the second times the derivative of the first. Okay, so what we've got here is, let's just simplify this a little bit.
Isn't log base 2 not the ln of 2?
What?
Isn't log base 2 not the ln of 2? For the...
I don't know, what was I doing? The second? Yeah, that's supposed to be a... Let me write that a little bit differently. You're right. Just to make it clear. Get the eraser. Okay. So it's the second times the derivative of the first. There we go. Thank you. Anyway, just simplifying that a little bit, we get x over the natural log of 2 times x plus, and then this is just the log base 2 of x. So the question is, so now because the mean value theorem, we gotta find, there's our endpoints 1 and 2. We gotta find the slope of those two things, the slope of those 2 points. So first we gotta find the first 2 points. When x is 1, what is the answer to this? So the natural log of 2, the log base 2 of 1. So 2 to what power equals 1? 0, right? 2 to what, what it's saying is 2 to what power equals 1. And that can only be a 0. So that's this number. And then when you plug in a 2, what's the log base 2 of 2? 2 to what power is 2? 1. And 2 times 1 is 2. So that's how you get the numerator. And then on the bottom, you just have 2 minus 1. And you can see, so this is the slope that we have to set our derivative equal to. And anyway, so then you set this whole derivative over here equal to 2. And then you can, you can wind up solving for x. Okay. So that's how that one works. So thanks for the question, Maria. You got to be careful when we don't get this very often, but when you get a log that's non-E, we almost always see ln. But when you see a log with a different base, you got to remember that. How do you take the derivative? Well, the derivative of a log is 1 over the thing you're taking the log of. So that's still this 1 over x that you see right here. But then the denominator also has to be multiplied by the natural log too. That's the thing that I find some students don't quite hang on to. So, questions?
Can we do a second derivative test question?
Okay, so we're talking about, let's see, on the assignment, that is where, like finding points of inflection?
Yeah. I mean, I'm more
Or
concerned also
the
with
ones
the
after it
intervals.
there.
Whichever ones have to do with like finding an interval.
Finding a what?
The interval where the
where
concavity changes.
the interval where it's concave up,
Yeah.
interval where it's, okay, let me just see what's on the next page here. Yeah, okay, so that would be in that section starting at can't figure out how to do this. So that's starting with number 43. Okay. So let's look at 47. All right, 47. Problem, 2x plus 18 over x, which you could rewrite as 2x plus 18x to the negative 1. All right. Use the second derivative. So this is, all right. Find all extrema. All right, so we're finding all extrema. So what the use of the second derivative is to help you determine if they're concave up or concave down. Yeah. So the first derivative is pretty easy. 2 minus 18x to the negative 2, which is 2 minus 18 over x squared. When is that 0? When 18 over x squared equals 2, if you just add this 18 over x squared to both sides, solve 2x squared equals 18, x squared equals 9. So at plus and minus 3 are something, extrema. If you use the second derivative, it helps because that tells you when is each, what is plus 3 a positive extreme or a negative extreme? So the second derivative turns out to be 36x to the negative 3, which is 36 over x cubed. Okay, so what's f double prime at plus 3? Well, at plus 3 cubed is 27, 36 over 27. It's a positive, so that tells me at plus 3 we have a relative min, because positive means concave up, and concave up has a relative min. At negative 3, we get 36 over negative 27, which means the second derivative is negative, therefore it's a max. So that's one way the second derivative test can be useful.
Could you go over that one more time? I'm still kind of confused.
Sure. So where do you want me to dig in?
Kind of after, I have up until like the first derivative parts when you started the second derivative test.
Okay, so you're okay with everything on the left side?
Yes.
All right. So all I did in this position is I repeated the first derivative. That's this written with a negative exponent. And then I took the second derivative. Second derivative of 2 is 0. Power rule for negative 18x to the negative 2 gives me plus 36x to the negative 3.
Yep.
Okay. So now what I didn't write here, let me change colors to red. So what you've got is what's f double prime at 3? Why 3? Because it's one of these two over here. At 3, you get 36 over 27. And I don't even care about the number. It's obviously positive. So that tells me at plus 3, because it's concave up, at plus 3, that must be a relative min. And then I did f double prime at negative 3, and that's 36 over a negative 27. And so that's a negative. So that tells me at negative 3, it's concave down, so we must be at a max.
Okay, so for relative extrema, you should use the second derivative test to determine.
Well, it just helps you nail down which is which. You know, it doesn't. We still found the extrema over here on the left.
Yeah.
But we didn't know which was which.
It might help if you draw out what you mean by it being concave up when it's a minimum.
Yeah, when it's okay. So when the second derivative is positive, it's concave up, which means it's shaped. It's shaped like this. And so that's got to be a min. And when it's concave down, it's shaped like this, and you got to have a max.
Okay.
Does that help?
Yeah.
Yeah.
Okay, thank you.
You're welcome.
When you're finding relative extrema, you can use the second derivative, first derivative, or the original equation? Does it just depend on the problem?
Yeah. You may not. I mean, it might be obvious to you that you have a relative min or a relative max, and then you don't need to use the second derivative. But the second derivative just helps you nail down which is it. Is it top of a hump or is it the bottom of a hump? That's the nice thing about that. Extrema are still found with the first derivative set equal to 0. Actually, there is, and maybe this is in a different part of the review assignment, there is another use for the second derivative, and that's to find points of, that's to find concavity. So if the problem says, what are the intervals of concavity for this? Well, then you've got to go to the second derivative. And so you might as well just go to the second derivative right away. And then when the second derivative is 0, that tells you, oh, we got a change of concavity called a point of inflection. So I don't know, hopefully that helps. So the second derivative can help you with extrema, as this problem shows. And it's absolutely necessary when somebody asks you a question about what kind of concave intervals do we have.
Yeah, I understand that, and I understand the concavity. I just, for some of the previous review problems, I wasn't sure when to use the first derivative or the original equation.
Oh, you mean when you substitute in?
Yeah.
Okay. I get the picture now. All right, so this is finding extrema. So when do you substitute in? So when somebody asks you a question about when is the function, maybe this is what you were thinking. When is the function increasing and when is it decreasing? Then you're going to find the first derivative, and you're going to, and when you substitute in your value, you got to substitute it into the derivative, because it's the increasing, decreasing that you need to find, and the first derivative tells you that. Positive, first derivative increasing. When it comes to concavity, if you needed to do concavity, then when you find your extrema, you're going to have to plug them into the second derivative. Let me see if hard to know where those are. Let me see if I can.
I understand the concavity stuff. It's also I don't know when to use the original equation.
When do you, I don't know what you mean when to use it.
Like when to like when you solve for x and then you put that number back into the original.
When to substitute into the original? Okay, when do you substitute into the original? When you need to find the y coordinate. That is not very common, but if somebody said to you, what is the relative max? Then you'd have to substitute back into the original function.
Okay.
You know, what's the y coordinate? So whenever they ask you for actual points and you need the y, which doesn't happen very often, that's when you would go back to the original.
Okay.
If they want to know what is the function increasing or decreasing, that's when you're going to plug it back into the first derivative. And if they ask you, when is the thing concave down or concave up, then you're going to have to plug it into the second derivative equation. I was just trying to find sample problems, but that have to do with your question.
That helps a lot, honestly.
Okay, good. I'm glad. Just going to see where questions on the review get into that.
Like if you could find one where we would use the original equation, that would be.
Well, okay, let's see what I can find. Well, right away from 1 to 8, find the relative extrema, okay? So when you do one of those questions, you're going to find the first derivative, set it equal to 0, and solve. We know that. Okay, that'll give you the critical points. But here, let's just go to one of those. 1 through 8. So, I don't know, let's look at number 2. Okay, so here's the problem, x cubed plus 6x squared, and here's the interval from -6 to 1. So find the first derivative, set it equal to 0, solve. X equals 0, x equals -4. Of course, the problem's not done because we need to also check the 2 points, -6 and 1. So that's what you're doing down here. And in order to find these y coordinates here, we had to plug it into the original equation, not the derivative. So when you plug in a -6, -6 cubed, 636, -216, and then you do 36 times 6 and you get +216, and when you add them together you get a 0. So that all happened in the original equation. So does that help? So there's a problem where you have to substitute back into the original equation.
Okay, thank you.
You're welcome. Yeah, let me remind you, I'm hearing silence for a little while, so I'm going to just remind you of something else. Remember, Rolle's theorem deals with a function where 2 points are of equal height, which I've circled here on the left. Okay? And it says, obviously, the slope between those 2 points is 0. So what it's saying is, if it's differentiable in between, there's got to be at least one place where the derivative of that function is 0. Blue line. Of course, you can't do it when there's a cusp. As a difference, the mean value theorem, the 2 points are not at equal heights, they're at a slope. And now it's simply saying, whatever the slope of these 2 points is, which we can calculate using the slope formula, again, if it's differentiable in between, there's got to be one place where the slope of that has to be equal to the slope of those 2 points. So Rolle's theorem, 2 points have to start off horizontal from each other. The mean value theorem, they can be at any slope.
Could you explain why they like? I guess why we learn the rules or the Rolle's theorem? Because you could technically just use the mean value theorem anyway, because it's saying that that's pretty much just saying that the derivative is going to be equal to the
You're
sum
right.
of
I
was.
mean, in effect, Rolle's theorem is a special case of the mean value theorem.
Yeah.
Yeah, that's a good point. And then the only difference is here. Okay, you could say you gotta calculate the slope, but everybody knows when you subtract 2 points that have the same height, you're gonna get a 0 for a slope. So yeah, you make a good point.
Okay.
Yeah. In effect, this is the one you really need, the mean value theorem. Yeah.
Could we do a couple problems with the limits of infinity?
Sure. Let's see. Where are those?
It's 55 through 64.
Thank you. Okay, I gotta find my way here. There we go. Okay. So, all right. How are we going to do number 55? X approaches infinity. Well, the limit of 8 as x approaches infinity is 8. And the limit of 1 over infinity. So, in effect, this is like if you're doing this problem. Oh, I can't write on here. But anyway, sorry. I just goofed this up. So, anyway, the limit of 8 as x approaches infinity is 8. The limit of 1 over x as x approaches infinity is 0. And 8 plus 0 is 8. Okay, 56. X is approaching negative infinity. Well, what's true of the degree of x, top and bottom? On top, it's a 1. On the bottom, it's a 1. So we have to go with the coefficients, right?
Mm-hmm.
So we have a negative 4 over a positive 1. But the x is approaching negative infinity. So on top, negative 4 times negative infinity is positive infinity. On the bottom, you're going to get a negative. So it's going to be negative 4. Hang on.
It's going to be positive because it's going to be negative. So you have to switch it.
I can't write on there. Okay. Here, let me copy this. Okay, so as we do this problem, so this comes down to really the limit as x approaches negative infinity of negative 4x over x. And now if you plug in a negative infinity, on the top you're going to get a plus, on the bottom you're going to get a negative, and so the answer is negative infinity. Right? Because this 1 and plus 1 on the bottom have almost no effect on the problem whatsoever. So let me So it's like the sign changes on the top and the sign changes on the bottom, and still negative.
Shouldn't it be the coefficients though? Shouldn't it just be -4 then? Because it's the same degree.
Yeah. So, okay, as x approaches negative infinity, on the top we're going to get this massively big positive number, right? Because -4 times a negative huge number is positive, honking huge. On the bottom, you're going to have a negative infinity, and a positive over a negative is a negative.
Mm-hmm.
So that's got to be your final analysis. So you can't, yeah, instead of just looking at the coefficients, when you have a negative infinity, you got to kind of think of the letter being there. You follow me?
Yeah, I'm still just not sure why you wouldn't just use the coefficients, being that they have the same degree.
You do. You do.
Okay.
But x is negative. So, I mean, yeah, you're right. It comes out the same either way. Okay, it's -4. But
It should be
oh yeah,
positive 4.
what did I do?
Yeah, it should be +4 would be the.
All right, so if you have negative infinity, that's going to be a positive huge on the top, and it's going to be a negative huge on the bottom. Positive over a negative is a negative, so that should be correct.
Okay.
So this idea of just look at the coefficients when it's tied, that's okay when you have a limit of x approaching positive infinity. But when you're approaching negative infinity, you got to kind of think of the coefficients as still being there. That's what I'm trying to tell you.
So if that question was on the test, you want negative infinity as the answer?
That is the only answer. Yeah.
Okay.
I thought it was a -4.
That's what I'm.
That's what I'm thinking Travis thought too.
Yes.
Okay. Hang on a minute. Yeah, you're right. It should be a -4. Thank you. But negative is correct. Yeah. Thank you. -4 is the limit. Yes.
Okay.
Yep. Okay, so where were we? Let's go back to those. Another problem. You pick out which one you want to look at.
How about 62?
All right, 62. So everything is a little bit different. To change the size here, you got to do this. Okay. So on 62, the degree on the top is 3. What's the degree on the bottom? It's really, in effect, 1, because it's a second degree, and then you're taking the square root of that. So do you follow? The top has a degree of 3, the bottom has a degree of 1. And so therefore the top wins. The answer is positive infinity.
Okay.
So when you got what you're probably thinking, what about the 2?
No, I mean, they're
So
kind of
dinky in
negligible.
comparison with x squared that you can just kind of, it dissolves.
Okay.
Yeah, just look at the power.
If this problem approached negative infinity, would it just be, the answer would just be negative infinity then?
Yes, and here's why. Because on top, a negative cubed is a negative. On the bottom, you've got a negative squared, which is a positive, and then you're taking the principal square root of that. So that be a negative over a positive. So the answer would have to be negative infinity. Did that make sense?
Not really. I
All
kind of
right.
lost you there.
All right, on the top. So you're saying what? Here, let me copy this too. Can't write on here, and so it's hard to. What are we doing? 62. Okay, so it's coming in here. So 62. All right. So you're saying rewrite the problem like this. Limit as x approaches negative infinity, x cubed over the principal square root of x squared plus 2.
Yeah.
Okay, so on the top, obviously we're going to have a negative infinity because a negative times a negative times a negative is a negative. On the bottom, you got a negative infinity squared, which is a positive infinity, and the square root of a positive infinity. And so, you know, you've got a negative over, I mean, obviously the top wins number-wise because you got a cube over something to the first. So we know the answer is infinity, and it's negative on top, positive on the bottom, so it's got to be negative infinity.
Okay, I think at first I was thinking that you do the square root of the bottom, so the degree would be 1, which then would make the negative, which then would make the denominator negative infinity. Does that
Say
make
that
sense?
again. So you got the first, oh yeah,
Yeah.
I got you. Yeah, do you see how I was reasoning there?
Yeah, so you want us to do it that way and not like how you'd solve for the other one, the
So I
negative.
got, what were you thinking again? Oh, that's a first degree.
Yeah, so I was thinking that's a first degree like as an x. So then I just used the negative infinity and inserted that for x and not x squared.
Right. But what's the principal square root of a negative? I mean, what's the principal square root of a positive? It's positive. So you still have a positive on the bottom.
Okay. I think I was just doing it where I already took the square root of it.
Oh,
So then
yeah.
the bottom was just x.
Yeah, I get you. Yep.
Okay.
Yeah. Instead of just thinking as the square root canceling out the x squared,
Yeah.
you got to remember that that square root on the bottom with no plus or minus in front of it means the positive square root.
Okay.
That's a principal square root. You're right. That needs to be. You need to think about that. Yeah.
Okay.
Okay. Let's go back. Any others here, Travis?
Can we use 63?
63. Okay. Let me grab that one. Okay. So, well, all right, let's just talk a little bit about cosine x for a few minutes.
Okay.
Cosine, as you know, only revolves between 1 and -1.
Mm-hmm.
So no matter, I don't care if you put an infinity in there, the cosine of infinity has still got to be something between a 1 and -1. So in effect, cosine of x has no effect on this problem.
Okay.
And so you really have, both have degree 1, 6x and x. And when you plug in a negative, you're going to have basically a negative. So it's going to be positive 6, right?
Mm-hmm.
Because you're going to have like -6 times infinity over negative infinity. Negative divided by negative is a positive. So that limit should be 6. So this part right here didn't really amount to anything.
Now, one question: with it being negative infinity, would it just be 6, or would it be negative 6?
It would be 6 because
Okay.
on top you've got a. Here's where you need to think of the variables. So really, this is negative 6x.
Oh, because it'd be a negative divided by a negative.
I'm sorry. Let me. That's not what I meant. This really comes out to. Sorry, I'm having trouble here. Negative 6x over x. Okay. Now, when you plug in a negative on top and bottom, what happens? Negative infinity becomes a positive 1, and you would just wind up with 6. So here's the case where I know it's the same old deal. When you plug in when you have a limit that goes to negative infinity, you can't really you can't just use that shortcut, can you?
Mm-hmm.
That's what it amounts to. Everybody, you get that, guys? So the shortcut was what? If the top and the bottom are tied, then just use the ratio of the coefficients. So you're probably thinking 6 over 1, but you need to think through also what's going on with the signs with x. In this case, it turns out to work. It's positive 6, but as opposed to what? This one up here, where we had, I guess this one, the rule would have worked too, wouldn't it? The coefficients, negative 4 over 1 would have worked. Yeah. Just think it through carefully when it comes to sign. Yeah. Let's see, going back to that page. Okay, so.
Could we do 61?
Sure. So, on top, what's the maximum that can be? What's the highest that the cosine of x can be?
Plus 1, or plus or minus 1.
5 times 1 is 5. So that's the highest the numerator can be. What's the lowest it could be? Well, cosine of x could be negative 1. And it would be 5 times negative 1. But so the problem is so this thing is hovering between 1 and negative 1. The bottom is going to totally dominate, isn't it? So it's going to go to 0 because the denominator is so huge compared to the top. That's going to be a 0.
Okay.
Okay. Another question? Oh, wow. I didn't realize what time it was already. Okay, good questions, guys. Oh, I see a request for 63.
We did that one.
Oh, we did.
Mm-hmm.
Okay. I just saw the request, Maria, but I guess we did it already.
Yeah, I happened to said the same one that she did, not looking at it. So
Okay.
So it worked out that way.
I had too many places to keep my eyes on. Didn't see that until last minute. I'm glad we did it. So let me just repeat the announcement at the beginning. There will be a study session tonight in our normal classroom, 7 to 9. She got permission from her supervisor to have it. So anyway, that's going on. And then looks like there's going to be a new, I don't know, I think that's a new in place of her tutor on Thursdays. I know that doesn't help with this test, but availability in the future. I'll be putting this announcement in an email to everyone. Okay, well, then I guess we're going to hang it up. Thank you. I appreciate your questions. Good job.
Thank you.
you.